Alright, let's get started with Lesson 2, Planck's Quantum Theory. Now that you have a pretty good understanding of electromagnetic waves, what they are and their characteristics, and understand the electromagnetic spectrum, we're going to turn our attention to the color of light and color in general and what we perceive as color with our eyes and brains. Now, there are two major ways in which we are able to see color. And you need to remember that we can only see light with our eyes in the visible region, and that is from, remember, 400 nanometers to 700 nanometers. Red light is 700 nanometers, and violet light is over in the 400 nanometer range. And then all the colors in between. So essentially the colors of the rainbow, those wavelengths and frequencies are what we can see with our own eyes. Any of the other electromagnetic waves in the electromagnetic spectrum we cannot see. So the first way in which we see color is pretty simple and straightforward. So we're going to use this diagram as a way to represent this first idea of color. We have a sun. The sun is going to emit light, all electromagnetic light, and that electromagnetic light, a lot of it will pass through our atmosphere and hit Earth. Now, the Earth has a lot of grass, as you know, and so grass is made up of different types of compounds or molecules. There are certain compounds in grass that will absorb some of the light, and others it's going to reflect and will not absorb it. So for instance, we have three colors here, red, green, and red, and grass will absorb red and blue color, but it will not absorb green. Green wavelengths and frequencies it will actually reflect, and that reflected green light is then picked up by our eyes and interpreted by our brain that grass is green because of the reflected light. So the first way, in other words, and how we visualize color or see color is through reflected light. Wavelengths or frequencies that an object cannot absorb but reflect, that's the color of the object we perceive. Another example is a tomato here. Tomato is red, and that is because the tomato's molecules will not absorb red light. It absorbs all the other colors but red. And so the red light is reflected back towards us, our eye, and to us the tomato will then appear to be red based on that reflected light. All right? So that is one way in which we see color. We could say the same thing for someone who's wearing a blue shirt. A blue shirt is blue to us because the molecules or atoms that make up that shirt are absorbing all the other colors except for blue. It's being reflected. Blue light is being reflected by those molecules, and therefore the shirt looks blue to us. All right. So let's talk about white light and black light and black. Okay. So white. Something is white because the molecules of that object reflect all the colors of the rainbow back towards our eyes. And so white light is a mixture of all those colors. And so that's why we view that the object is white, because we're seeing all the colors. Whereas black is the absence of light. That means that all the molecules that make up that object are absorbing all the colors of the rainbow, and no light is being reflected back towards us, so it appears to be black for us. Think about your countertops for your lab tables. They're black, and that is because the materials that the table are made out of absorbs all the colors of light and reflect nothing back towards us, so it appears to be black to us. All right, this leads us to the idea of black bodies then. Now, a black body is an object that absorbs all light. all electromagnetic waves, everything from radio to gamma rays, and will not reflect or emit any radiation or any light back towards us. All right? And so black bodies are very rare to find some kind of object that will actually absorb all light and not reflect or emit any light back towards us. All right, now we've talked about reflective light, and we mentioned just a minute about emitted light. All right, so there's a difference between reflected light and emitted light. Reflected light, again, is light that is being bounced off of molecules because it wasn't absorbed by those molecules. But emitted light is different. Emitted light is light that is actually being emitted by atoms or molecules in a material. And so emitted light is another way in which we can see color. Let's give you an example. All solid materials emit electromagnetic radiation, all of them. And the amount of electromagnetic radiation is going to be determined by the temperature of that solid material. All right? In most cases, the solid materials emit a lots of invisible infrared radiation. All right? Now, infrared, remember, is not in the visible region, so we can't see that. So, lots and lots of objects give off infrared. Another word for infrared is heat energy. All right? It's infrared radiation that gives objects their heat, and then they radiate their heat signature or whatever, including your own bodies. The atoms and molecules in your body emits infrared radiation, which heats up your body or heats up the surrounding air around you. Now, as the temperature increases, that means as those atoms gain more and more energy, then we start emitting different types of light. So, for instance, at 750 degrees C, a solid is going to emit a bright red light, and you can think of that like a or think about a red hot fireplace poker. As you put it in the fire, that solid object gains more energy, and then the atoms are going to begin to emit red light, lots of it. Okay? Now, as we begin to add more and more energy and the temperature begins to raise, then we'll start seeing yellow light and then blue light, and then finally, at about 1200 degrees C, you're going to see a solid glow of white light. Now remember that white light means that all the colors are being emitted from the solid object. All right? So the wavelengths, and this is a really important statement here that's in your notes, and so you might want to highlight this. The wavelengths of emitted electromagnetic radiation depends only on the temperature. All right? So over here we have an object here. This is a solid object. And notice that this solid object is emitting various colors. And each of those colors that are being emitted depends on the temperature gradient of the solid object. So think about which one of these colors being emitted, or which part of this solid object is going to be the coolest. If you said this end, you would be right. The kind of the black end. All right. Now there is light being emitted from this end, but it's going to be emitted as infrared. Okay, so you can have lots of infrared in that region. And then as the temperature increases, we get the red light, and then we get the yellow, and then finally we have the glowing white light, which tells us that all colors are being emitted at that time. Okay? Now, this was quite a mystery to scientists early on, is about the light being emitted from atoms in these solid objects. And so there's quite a bit of studying going on. Why do we see these different colors being emitted at different temperatures? All right. All right, here's another example. Here's a nice metal spring. We can see that there's a temperature gradient here. Down here at the very bottom is going to be the coolest temperature, and all we're going to see emitted really here is coming off as wavelengths that are infrared, which we can't see, so it appears black to us. And then as the temperature increases, we get more red light coming off of here. So red light, or red electromagnetic waves. And then we get orange. And then finally we get yellow coming off of here. Some yellow. Alright? At those different temperature gradients. Alright? Now, that is what we saw until we looked at the spectrum of light that was coming off of these objects, and something unique was happening, which we'll get to in just a minute. Alright, so here's a table, and the surface of this table is black. So basically what I want you to think about is this, is that the light that's coming in to this table, all the light, okay, so light is being absorbed by these molecules, every bit. And the reason why we know it's being absorbed is we're not seeing any reflected light. There's no reflected light, so the table looks black to us. But the question is the table emitting light? And the answer is yes. All the atoms are emitting light. The reason why is because those atoms are moving in that table. Okay, it's a solid object, so there's not a lot of movement, but there's vibrational movement. And because those atoms are vibrating, vibrating atoms are going to emit electromagnetic radiation. And we know this because we talked about that all matter contains charged particles. And charged particles, when they're vibrating or oscillating, is going to emit electromagnetic radiation. So this table is absorbing all the light, but that light that's being absorbed is causing the atoms in this table to vibrate or to oscillate. And as those atoms are oscillating, they're going to emit electromagnetic waves from this table. But the question is, what are those electromagnetic waves? What's their wavelengths and frequencies? Well, it turns out that they're in the infrared region. And you remember, we can't see infrared light. So to us, the table still looks black because there's no reflected light, and the only emitted light is in the infrared region, which we can't see. All right? So I hope you understand this. If you need to take some time to go back and to really study this idea of the difference between reflected light and emitted light, I would. It's an important difference. All right. So before we get into the greenhouse effect, let's just summarize something really quick. Reflected light is being reflected off of an object because the atoms will not absorb that light. And if it is in the color region, then we can detect a specific color. All right? But atoms in an object that absorb energy, such as light, those atoms are going to vibrate. And vibrating atoms themselves will emit electromagnetic radiation or light itself. All right? And so as you heat up an object, it's going to start emitting more and more different types of electromagnetic radiation, and some of that is going to actually be color, like the heated object, the heated metals that we saw with the fire poker or whatever, and you start seeing reds and then oranges and then yellows and then blues and then finally all the colors by the white light. All right? So kind of hopefully see those differences now. Okay, so what we're going to turn our attention to is some applications of all of this. Okay? And the first application we're going to look at is known as the greenhouse effect. All right? Now, the greenhouse effect deals with emitted light. It will deal with reflected light, absolutely, but a lot to do with emitted light from the surface of the earth. Okay? So what essentially happens is the sun is going to release a whole bunch of light towards Earth, and we know that. Now, when this light hits our planet, a lot of that light is going to be reflected back out into space, all right, because of our atmosphere, all right? The atmosphere causes some of the light from the sun to be reflected. Especially like gamma rays, X-rays, that kind of stuff is usually reflected back into space. But some of the light definitely gets through, especially in the visible spectrum, which is good because that allows us to see color, as well as some UV light, and that's what causes sunburns that we get from the sun. Like when we go tanning or whatever, that UV light that penetrates the earth and hits us causes the sunburns or the tanning that occurs. So the bottom line is there's a lot of light that hits the earth. Now, some of the light that hits the earth is reflected, and that reflected light then creates the colors all around us of objects on this planet. But a lot of the light gets absorbed, and the molecules in the Earth's surface then begin to vibrate more rigorously. All right. So let's look at this. Let's say that we get a lot of light that's penetrating here the Earth, and the molecules that are in the Earth's surface are going to absorb all of that light, or a lot of it. Okay. We're not counting the reflected light, just the absorbed light. Now that absorbed light is then going to speed up the vibrations of the molecules and atoms that are in the Earth's surface. And when it does so, those vibrating atoms are going to begin to emit radiation. And it's usually radiation that is in long wavelengths, and they are infrared. Okay? So all of this is infrared that's coming up here. Okay? So the atoms in the Earth then are emitting infrared radiation. Now, that infrared radiation is going to go up into our atmosphere. However, those longer wavelengths of infrared radiation cannot penetrate the atmosphere. So what does it do? It comes back down. All right? And so remember, we said that infrared radiation is really heat energy. And so because that infrared radiation is being reflected back towards the Earth, it's going to heat up the Earth. And this causes the temperatures, the mild temperatures on our planet, is through the greenhouse effect. Okay? So here we kind of see a bigger idea. Again, we have solar radiation that's coming down. Some of that is reflected light that goes back out in space, but others light is being absorbed, okay, by the atoms and the molecules that are in the surface of the Earth. And then those atoms are emitting the infrared radiation that we see here, infrared, which is essentially heat. Now, in the atmosphere, we have certain gases that we call greenhouse gases. The big ones are water, carbon dioxide, and methane. Okay, again, water, carbon dioxide, and methane are greenhouse gases. I would like you to know that. Now, these greenhouse gases are what's going to cause infrared radiation to be reflected back down to Earth. And that is what's going to heat up the Earth. So right now we're kind of on this big global warming phase in our planet, or this idea, and that's because they're saying that there's a lot more CO2 that's in our atmosphere, and a lot of it they say is human cause, okay, or humans are causing more CO2 to be in the atmosphere, and what this does is causes more infrared radiation to be trapped on Earth, and so therefore it's causing the Earth to warm up. Okay, so that's kind of the idea there with global warming. You can see the same thing going on here in this space diagram, where you have infrared radiation coming out towards the atmosphere, but it gets reflected back down to Earth. See all of this and so forth, warming up the Earth and so forth. Alright, now the greenhouse effect can also occur in our cars. Now, our cars have windows, and that windows will allow a lot of the light to pass through the windows. But inside of the car, the materials like the seats and other things, the dashboard, whatever, is going to absorb all of that light that's coming in through the window. And those atoms that are in the seats or the dashboard or steering wheel, they're going to start vibrating more rigorously. And as they begin to vibrate, then they're going to emit infrared radiation, just like we saw that the Earth does. But the window will not let infrared radiation out. So the windows stop infrared radiation from being exiting the car, and so all that infrared stays in the car and then heats up the car nicely. All right. That's the way our heaters work in our car too. So we let all of that heat in, and it gets trapped because the windows won't allow it to escape very well. All right, and we also do that with plants. We have greenhouses that are made up of glass, so it allows wavelengths to enter, or light to enter the greenhouse through the glass, but then the atoms and molecules inside of the greenhouse are going to emit infrared again, and that infrared is stuck in the greenhouse, and that warms up the greenhouse to allow plants to grow even in the wintertime. Alright, now this is one of our big kickers here, and we're going to spend a lot more time in class on this diagram here, a little bit more. What I want you to take away with this for right now is to look at this graph. Down at the bottom we have wavelength, and on the y-axis we have intensity. And what I want you to think of intensity as is brightness. Okay, the brightness of the light being emitted. Okay. Now, remember we said that emitted light, the type of emitted light, is temperature dependent. So depending on the temperature of the object will depend on the type of electromagnetic radiation that's being emitted. All right? So at 300 Kelvin, we get a graph like this. All right? Now, that tells us that most of the light that's being emitted is in the infrared region at 300 Kelvin. So if I heat up a solid object to 3,000 Kelvin, you're mainly going to get infrared radiation being emitted. There is a small sliver of red light being emitted, but most of it is infrared. And this peak right here, right there, is the highest intensity peak. So it's going to be the brightest part of the light that's coming off of there, and that brightest part of the light is infrared. All right, and so therefore we can't see any color really at 3,000 Kelvin. But what happens when we increase the temperature to 4,000 Kelvin? So at 4,000 Kelvin, we get a spectrum that changes like this and drops down in the ultraviolet region. Okay, so we get a broader spectrum. We get a lot of infrared radiation coming off in this section here. This is all infrared, but now we're getting some visible light. All right, at 4,000 Kelvin, we're getting a lot more visible light coming off of there. Not a huge amount, but still, we're going to start seeing some reds, more reds coming off of that solid at that deal. But we're also getting some UV light coming off of there. Now, we're not going to see the UV light, but a little bit but will generate. Now, if a solid object is heated up to 5,000 Kelvin, now we're really going to radiate some visible light at 5,000 Kelvin. So at 5,000 Kelvin, the max peak, intensity peak, is in the red region in the visible spectrum. So we're still getting infrared coming off, but now we're getting a lot of light being emitted, a lot of intense light being emitted in the red region, and so the object is going to start appearing red to us, and it's really going to be emitted red, glowing red light, okay, at that maximum intensity peak. Now if we get it up to 6,000 Kelvin, right, we're emitting a good range of colors from red to all the way to blue. At this maximum peak, we're emitting all the colors in pretty much equal fashion, and therefore it's going to be white light at this point. So we're going to see a lot of white light at 6,000 Kelvin. We're still getting infrared coming off in this region here, but we're getting a lot of visible light, so therefore it's going to appear white to us at 6,000 Kelvin. Now, but you can also see we are going to get some infrared, all right, or some UV light down over in this region here. So we get visible, infrared, and ultraviolet at 6,000 Kelvin when we heat up a solid. Now, one of the takeaways of this graph is that no matter what we do, raise the temperature, no matter how high the temperature gets raised, we will always have a crash point in the ultraviolet region. So even if we add another spectrum here, it's going to crash in the ultraviolet. No matter what we do, it's going to crash always in the ultraviolet. What that begins to tell us is that atoms cannot emit energy outside of the ultraviolet region, which tells us that atoms have a limitation to the amount of energy that they can emit. All right. Now remember, energy is going to increase as we move in this direction from infrared to visible to ultraviolet. Ultraviolet is going to have more energy being emitted than the visible or the infrared region. So you got these vibrating atoms that are vibrating, and they're emitting electromagnetic radiation in the infrared, in the visible region, and in the ultraviolet region. But they cannot have the ability to emit electromagnetic radiation past the ultraviolet region. They can't emit X-rays or gamma rays at all. Okay? They're just not able to do so. All right? So we're going to spend more time on this graph in class. So this is just kind of get you an idea of this idea. All right? Now, I think what we'll do is we'll end here. I think this is a good stopping point, and then we'll pick the rest of this up in class. Okay? So make sure you review through these ideas. If you need to rewatch this lecture video, do so. But prepare for a quiz. And that is it for now.